This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, the professor for this class, and we're at lecture 47. We're still on our series on lithography, but this time we're going to look at how light propagates into a photoresist and how it creates standing waves and a related phenomenon called swing curves. Standing waves are really quite common in the world. We see them all the time. We may not recognize them as standing waves, but whenever you blow over the top of a half-filled bottle and get a characteristic tone resonance in that bottle, you're creating a standing wave. Pipe organs work by creating standing waves of air pressure inside of the pipes. When you pluck a guitar string or violin string or any stringed instrument, you're sending a wave down that string, which then reflects off of the fixed end of the string, comes back, and interferes with the original vibration to create a standing wave, which creates the characteristic tone for that string. So standing waves are everywhere, and they're present in lithography as well. It happens when we expose. We've talked about, for the last several lectures, how to create an image that is projected from the imaging tool onto the photoresist. But of course, the image that we're projecting doesn't stop when it hits the top of the wafer. It travels into the photoresist. And of course, we need that we need that pardon me, we need that to happen in order to create an exposure inside the photoresist. But if this light is propagating through the resist, what happens when the light reaches the bottom of the resist? Well, if the substrate or the film stack below the photoresist is reflective, well then some of that light from the image will be reflected back up and will travel up through the resist. Now I've got light going down, a wave going down, and another wave going up. The interference of those two waves, the interference of two waves propagating in opposite directions, creates a standing wave. So if I have a photoresist, now I think of this, my wafer is kind of tilted up sideways. So here's my substrate, my photoresist, and I have light coming in, traveling down through the photoresist, hits the substrate, and some of that light is reflected back up. I have a wave, a traveling wave going down, a traveling wave going up, and what I create inside the resist in the intensity is a standing wave. Now it's called a standing wave because of a very significant difference between that and a traveling wave. In a traveling wave, the peak of the sinusoidal wave moves with time and through space. So the peak doesn't just stay in one place. As it travels, at any point in space, the electric field goes up and down and up and down. And if I look at the peak, it's traveling, it's moving forward. But with a standing wave, the peak is fixed in one position. It sits right there the whole time, it never changes. Same thing for the valleys. And this is caused because of interference. But not interference of two waves traveling in the same direction. We get a standing wave when we have interference traveling in opposite directions. And you could figure this out by adding up two waves if they're traveling in opposite directions. What happens in photoresist is the standing wave is printed on the sidewalls of the resist image. So here are some resist images. Some friends of mine at Motorola gave me this image, which I appreciate, and it shows, it's an eye-line exposure. Remember, that's 365 nanometers, and it shows standing waves through the resist. This scalloping is characteristic of imaging standing waves. This is not good, but the worst part about it is this foot. That is, the bottom standing wave almost always is the biggest one, and this can really impact pattern transfer down into the photoresist, into the substrate when we do an etch. So the standing wave pattern inside the resist looks like this. You see that it is sinusoidal. In fact, there are three interesting characteristics of the intensity of light through the depth in the resist. So up here is the top of the resist at z equals 0. Down here is the bottom of the resist. You can see I have a thick 900 nanometer resist. And this happens to be an eye-line exposure, if memory serves me right. Three important characteristics we'd like to understand. What is the period of the standing wave? Peak-to-peak distance in the thickness of the resist. What controls the amplitude? Now, if I can make the amplitude smaller, then the standing waves would have less of an impact on my lithography, on the pattern transfer. So what controls the amplitude of the standing waves? The distance in intensity from the bottom to the top of a cycle or a half cycle. And finally, notice this gradual decline in the mean value of the sinusoid. This must have something to do with the absorption of light, but I'd like to understand what controls this decline in the average value. Well, we can answer all of these questions by mathematically calculating the standing wave pattern. We're not going to have time to go through the derivations at all. They are in my lithography textbook, Fundamental Principles of Optical Lithography, if anyone is interested. But here's the answer. The intensity, I leave out a proportionality constant, but the intensity is proportional to this quantity. And from this, we can look at all of those characteristics that seemed interesting to us. First of all, some of the parameters. R is the reflectivity of the substrate. So capital R is the intensity reflectivity, and it's a function of rho 23, which is the electric field reflectivity. I take the magnitude of that squared, and I have the reflectivity of the intensity. Alpha is the absorption coefficient of the resist. D is the resist thickness. Another important parameter is the refractive index of the photoresist, N sub 2. Lambda is the wavelength, and then finally phi 23 is the phase change of light upon reflection. So, there's an equation. Okay, what can I do with this equation? Well, I can answer all three of the questions that I just had. What determines the period of the standing wave? Well, we remember our trigonometry and know that if I have a wave, the period of a sinusoid, I put it in the form of 2 pi x divided by the period. Therefore, the period, just by inspection, is going to be the wavelength, lambda, divided by 2 times the index of refraction of the photoresist. So that's what determines what the period is. So, for example, if I have eye line, 365 nanometer wavelength of light, typical refractive index of a photoresist is about 1.7. So the period is on the order of 105 or 110 nanometers. Now, the other interesting thing I'd like to know is the amplitude of the standing wave. Well, that's this term, the term in parentheses that multiply the cosine. And we see exactly what controls the amplitude. We have the reflectivity of the substrate. In fact, it's the square root of the reflectivity that matters. And then e to the minus alpha d. What is that? E to the minus alpha d is the total absorption of the light that makes it to the bottom of the resist. So alpha is the absorption coefficient. D is the thickness of the resist. E to the minus alpha d is the fraction of the light that starts at the top that makes it to the bottom. So it accounts for absorption. And finally, the average intensity as it varies through depth in the resist is this term out in front, this whole big term here. It's got e to the minus alpha z, that's accounts for absorption as it travels down, and then r e to the minus alpha 2d minus z. Well, that's absorption of the light traveling up after it's reflected. So I'm adding two absorption terms, a term going down and another term going up. And that's it. Once we can mathematically derive, using the physics, the optics of light and how it is transmitted and reflected at interfaces, how it's absorbed, and how it interferes, I can derive an equation that gives us a lot of information. In particular, it will give us information about how we can get rid of standing waves. If I wanted to get rid of standing waves, what would I do? Well, I'll take this equation and look at the terms and say, what terms allow me to reduce the standing waves? One term is right here, alpha. What if I made alpha bigger, or in particular, alpha times d bigger? Alpha, the absorption coefficient, d, the thickness of the resist. If I make that term bigger, then e to the minus alpha d gets smaller. And if this gets smaller, the amplitude of the standing wave gets smaller. I generally do that by adding a dye into the photoresist, an absorbing dye that increases alpha. And this is reasonably commonly done, especially in older technologies. We would frequently add dye to our photoresist to reduce the standing waves. But I see another term, R. How can I decrease R? To decrease the substrate reflectivity, I could use a bottom antireflective coating. Well, here's a simple way of saying it. Well, I could paint the substrate black. Silicon's a pretty good mirror. If you've ever seen a silicon wafer, it's very reflective. And then, of course, we do lithography on metals as well. Very reflective materials sometimes. If I were to just take some black paint and coat the wafer, my reflectivity would go down dramatically. Of course, black paint doesn't sell for as much as anti-reflective coatings, so we don't call it black paint. In fact, it's much more sophisticated than just black paint. Black paint would be absorbing, but we also want to match the refractive index and do what we can to absolutely minimize the value of R more than we could with just absorption in an underlying layer. We call these materials bottom antireflective coatings. And they are, in fact, the most common way of reducing standing waves. And we'll see that it has some other benefits as well. We could use a range of wavelengths or a range of angles incident on the photoresist. We haven't talked about angles. This equation was derived assuming normally incident light. But let's talk about wavelengths. We recall that the period was lambda over 2 times the refractive index. If I use a range of wavelengths, I get a range of periods. A range of periods means my sinusoidal positions of the peaks and the valleys don't match up. And if I add together, superimpose a bunch of sinusoids at different periods, they tend to cancel out the variations. So broadband illumination has reduced swing curves, or excuse me, standing waves. And finally, I could try to smooth out the standing waves after the fact with something called a post-exposure bake. I'll talk about that next. All of these techniques have been used over the years, and some of them are more common than others. The most common one today, especially for all state-of-the-art lithography, is the bottom antireflective coating. We always use a bottom antireflective coating. In older processes, we might try some of these other techniques simply because they're cheaper. Bottom antireflective coatings are expensive, and adding dye to a photoresist or using a post-exposure bake is a much cheaper way of reducing the standing waves. The difference is they tend to be able to reduce the standing waves, whereas the bottom antireflective coating could almost completely eliminate a standing wave if we do it correctly. So, post-exposure bake, what does that mean? What that means is after exposure, but before we develop, we throw the resist onto a hot plate, the resist-coated wafer onto a hot plate, and we bake it. This allows the exposed and unexposed material, something called a photoactive compound, which we're going to talk about when we get to photoresist chemistry. But the exposed and unexposed material can diffuse, and as such can smooth out the standing waves. You know, you can think of the standing wave pattern as a concentration gradient of high and low levels of exposure. And if we allow diffusion, the exposed material can move into the unexposed regions and vice versa, smoothing out the standing waves. We can use the time and the temperature of the bake to adjust the diffusion length. But we have to be careful. Our goal is to smooth out the standing waves. But if we have too much diffusion, we'll smooth out the features that we're trying to print. After all, those create exposed and unexposed regions as well. As such, our goal is to find a diffusion length. I'll call it sigma sub d, the average distance that a particle will diffuse during this bake. We want the diffusion length to be on the order of or bigger than half of the standing wave period, so that things will diffuse all the way from the peak down to the valley. That's diffusing away the standing waves. But this diffusion length must also be significantly less than the minimum feature size. If the diffusion length starts approaching the size of a feature, then it will wash out the feature we're trying to print. Well, for a long time in lithography, we were able to thread this needle. For example, if we have I-line, standing wave periods on the order of 105 or 110 nanometers, so we would need a diffusion length that was on the order of 60 nanometers in order to smooth out our standing waves. If I was printing feature sizes that were above 500 nanometers, well, then that works. A 60 nanometer diffusion length, 500 nanometer feature, that's enough smaller that it's not going to have a significant impact on the feature size. Well, as we have shrunk the feature size over time faster than we've shrunk the wavelength, and therefore faster than the standing wave period. If we look at a 193, well, let's just do 248. 248 exposure, the standing wave period might be 75 nanometers, so we need a sigma sub d, a diffusion length on the order of 40 nanometers. But we've used feature sizes down to 150 nanometers, maybe even down to 130 nanometers with 248. Now I've got a 40 nanometer diffusion length and 130 nanometer feature size. That's only a factor of 3, not a factor of 10 like we were talking about before. Now the diffusion length is a fairly large fraction of the feature size, and it starts to degrade the quality of that feature. As a result, by the time we switched to 248 nanometer lithography, we stopped using post-exposure bakes as a method of reducing standing waves. In fact, we didn't stop using post-exposure bakes, we just didn't use them to increase the diffusion length and smooth out our standing waves. Instead, we switched to using anti-reflective coatings almost exclusively as our method of reducing standing waves. So let's review what we've learned. Standing waves are caused by interference of incident and reflected light. Standing waves can cause the scalloping of the resist sidewall, and this reduces our ability to control the CD. I'll remind you, CD is one of the most common acronyms in lithography. It means critical dimension or line width. Scalloping reduces our ability to control those line widths, especially at the resist substrate interface, and especially when it comes to transferring that pattern in an etch process. We saw that a mathematical description of the standing wave, which I just presented the final equation without going through the derivation, was very useful in understanding the phenomena. We could look at the equation and extract not just a description, but an understanding of what's going on. Use that understanding to guide decisions about how to reduce standing waves in particular. We found that there were 4 ways to reduce the standing waves. Decreasing the substrate reflectivity using a bark, the most popular way today. Increasing absorption using a dyed photoresist, a popular approach in the past because it's lower cost. Using broadband exposure, a range of angles or a range of wavelengths. And after the fact, by using a post-exposure bake. Now, 2 more topics related to light propagating into a resist and standing waves. A related but different phenomenon is called a swing curve. We have found, through experience, the hard way, and then it became obvious when we thought about, but we found that some lithographic parameters varied in a periodic way with resist thickness. For example, if I were to measure the line width of a feature and vary the resist thickness, here I show resist thickness varying from 900 nanometers to 1200 nanometers, and I looked at the line width, I would find a sinusoidal variation in that line width. This sinusoidal periodic variation happens to have a period exactly the same as the period of our standing wave. which makes you think, oh, this must be something related to that, some kind of an interference phenomenon. And in fact, that's what it is. It's a different interference than what goes on inside the resist. It's an interference of the incident light and light that's reflected out of the resist, off the top and through the light that comes out of the resist after it's traveled through the resist. This interference phenomenon changes the exposure dose that the photoresist sees periodically with resist thickness. The result is this line width variation. Well, if we look at the magnitude of the variation, we see that it's more than plus and minus 10%. Now, lithographic rule of thumb, our goal is to control the line width to plus or minus 10%. Well, what this says is if we have large enough thickness variation in the resist, we're going to eat up our entire budget of line width variation without worrying about all the other things that can go wrong in our lithography process. This is clearly unacceptable. What can we do? Well, we could try to control the resist thickness to better than a period, half a period of this swing curve. In fact, we could try to make the resist thickness control extremely tight. And that's possible to do. Our spin coating is actually quite good. We can get resist thickness control that's quite good. Then, if we have good resist thickness control, we'll pick the proper thickness. Now, take a look at this curve. What thickness would you pick? If you could pick any resist thickness, you're designing your lithography process, and you can pick any resist thickness you want, what would you pick? Well, I would pick a thickness that was at a minimum or a maximum of the swing curve. And the reason is simple. When I'm at a minimum, small variations in resist thickness produce the smallest variations in line width. Same thing for a maximum. If I'm at a maximum, small variations in resist thickness produce small variations in line width. The extrema are the least sensitive. Now, if I happen to have a resist thickness of this, a small variation in resist thickness would produce a large variation in line width. That would be terrible. So I always operate at a minimum or a maximum of the swing curve. But that assumes I can control the resist thickness. And I can, as long as my wafers are flat. But as soon as I start coating over topography, then I have real problems. Right? I might be able to control the resist thickness on the top of the topography or on the bottom of the topography, but look what happens as I go over a step. The thickness gets very thin, and then it gets very thick, and then back to normal. I can often get resist thickness changes over topography that exceed a half a period of the swing curve. When that happens, I am guaranteed to have big line width variations. So let's take a top-down look at a feature. So I'm going to take a feature and go over the step. And here's a top-down. My black line here shows me the bottom of the step. Here's one example. Suppose I pick the nominal resist thickness to be a maximum of the swing curve. What that means is all variations in line width will produce lines that are smaller because I'm at the peak. All thickness variations make the line width smaller. So if I pick a resist thickness at the swing curve maximum, as soon as I start going over the step, the line width shrinks, and it shrinks, and it shrinks. So I have all these notches in the lines that make them smaller. Well, that's not good. It's also not that good if I pick the swing curve minimum. At a swing curve minimum, all errors in resist thickness make the line width bigger. And so I get these bulges in the lines. Well, which of these is better? It kind of depends on what you're making. Sometimes you're more sensitive to line widths that get too small. Sometimes you're more sensitive to line widths that get too big. So it depends on the exact patterns that you're printing, which of these you might choose. Of course, it would be better to have neither of these phenomena occurring, and we can eliminate the swing curves using a bottom antireflective coating, just like we could eliminate the standing waves. So that tends to be what we do whenever this phenomenon is important. One last, oh yes, so we use a bottom anti-reflective coating to reduce the swing curve, but there are some other approaches too. Resist absorption, adding a dye, also reduces the swing curve. Using broadband illumination or a range of angles illuminating the resist also reduces swing curve. So these three phenomena which reduce standing waves also reduce swing curves. But we have a fourth method, what's called a top anti-reflective coating. This is a coating that maximizes the light transmitted into the photoresist and reduces any interference because I don't have any reflections off the top of the photoresist to interfere with. Top anti-reflective coatings can be used as well. And notice that a post-exposure bake is not helpful. Post-exposure bakes do not help us with swing curve at all. The best solution is the bottom anti-reflective coating because it's the solution that both reduces swing curves and reduces standing waves. And again, a well-designed bottom anti-reflective coating can essentially eliminate both of those phenomena, whereas resist absorption, a dyed resist, can only reduce them somewhat. One last phenomenon to worry about, something called reflective notching. In the previous example, I had a line going over the step. So the line starts at the top and then it travels down over the step. So the line was traveling in this direction. What if I have a line that's perpendicular, perpendicular to the page or the screen here and is traveling parallel to the edge of the step? So here's the edge of the step right here, and I have a line going parallel to that step. What can happen? Well, if this step is at all reflective, when I shine light down to expose the resist in the region of the step, it can reflect off of the step and travel in a direction that I do not intend. If I have a feature close by, I can actually expose a region of that feature and make it soluble when I did not intend it to be. The result can be a notch that is eaten out of the edge or the side of a photoresist profile, something we call reflective notching. Here's an image that illustrates that. So I've got a pattern with topography, and these are little dimples, little dents, as I coated the wafer with some material. Maybe this is polysilicon, which is moderately reflective. I have these little indentations, and now I'm trying to print a resist line over the top. What happens is these little indentations take the light and reflect them into a pocket here that creates a notch. So every dimple creates its own notch. Here's a dimple, here's a notch. Here's a dimple, here's a notch. Because of this phenomenon of light reflecting off of the sidewall and creating a notch in the resist. This can be very damaging in terms of getting good control of the features. What can we do to fix it? Well, the same thing we've done before. A bottom anti-reflective coating. It's about the only thing that is effective at fixing these reflective notching problems. So as we can see, bottom anti-reflective coatings cure a lot of ills, and that's why they're universally used in advanced lithography processes today. So what have we learned in lecture 47? As always, you should be able to quickly and easily answer these questions. If not, please go back and review the material to make sure you understand it. What causes a standing wave? Why are photoresist standing waves bad? What are the detrimental aspects of having standing waves on a photoresist edge? Name 4 ways to reduce standing waves in resist. Which one of these ways is the most commonly used today for advanced processes? What is a swing curve? What is reflective notching?